Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we have seen the speed control of a separately excited or shunt excited DC motor. We will briefly review that and go forward. So, this is the speed torque characteristic of separately excited DC motor. The speed is omega m, that is equal to the terminal voltage V by k phi, phi is the field flux, minus the resistance R, the torque of the motor by k phi whole square. Now, this characteristic is a straight line. So, we have various methods we discussed in the last lecture. We can go for armature resistance control, where we control the value of R here. Now, when we control the value of R, the slope of this characteristic changes, and this in this way we can control the speed. This is the speed corresponding to the first characteristic. This is our load torque T L, and the intersection of the load torque with the motor characteristic gives us the operating point. Now, this is the first operating point corresponding to the resistance R 1, the armature resistance R 1, R equal to R 1 here, and when we make R equal to R 2, the characteristic is the second one, and this intersection is at this point, and the corresponding speed is omega m 2. So, the speed decreases, speed is in the y axis, the speed decreases. Now, when we make the resistance equal to R 3, we increase the resistance and the resistance becomes R 3. The intersection of the motor characteristic with the load is here, and in that case the speed is omega m 3, it decreases. We further increase the resistance to R 4, R equal to R 4. So, the speed reduces here further. So, this is how we control the speed. Now, when we insert resistance in the armature, we have more I square R loss, because the armature carries full amount of current. So, this method, though quite easy to implement, you can have a rheostat in the armature and go on varying the armature resistance, the speed will change, but this method is not an efficient method. So, the problem with this method is I square R loss increases with increase in R, increase in resistance. Now, we go for the second method, which is the armature voltage control. Now, in the second method, we have the same speed torque characteristic. What we do here, we control the armature voltage. Armature resistance is kept constant, we do not change the armature resistance, this is at the minimum value, and then what we do here, we change the applied voltage V. The applied voltage when we change, if you remember, this was the motor, and we have the field here, and we apply the voltage here V. But in this case, what we do here, this is a separately excited motor, we excite the field separately. We apply a constant DC voltage here. So, the field current is almost kept constant, the field resistance. So, IF is constant, and having IF constant, this armature resistance, the armature circuit resistance, what we do here, we vary the applied voltage. So, we vary this V. Now, when we vary this V, this is the current which flows through the armature I A. Now, when we vary the V, the no load speed changes, V by K phi changes, the resistance is constant, we do not change the resistance, the voltage is changed. So, the no load speed changes here, this is the no load speed and this is omega m naught 1. So, the no load speed changes corresponding to V 1, V is equal to V 1, we have omega naught 1. Now, when we decrease the voltage V, the slope remaining the same, this is the slope remaining the same, the no load speed changes, here it is omega m naught 2. Now, further we decrease the voltage. Now, when we further decrease the voltage, the speed becomes omega m naught 3, we further decrease the voltage, the speed becomes omega m naught 4. So, when the speed decreases, we see that when the voltage decreases from V 1 to V 2 to V 3 to V 4, the intersection also changes. This is the intersection of the load characteristic T L with the first motor characteristic. So, the corresponding to V 1 the speed is omega 1, corresponding to V 2 the speed is omega 2, and then when we further reduce the voltage, the speed decreases and this becomes omega 3, and then when we further reduce the voltage, the speed again decreases and we get omega 4. So, this is how we control the speed of the motor. Now, in this case we do not vary the resistance, the armature resistance is at the minimum value. So, this is more efficient than armature resistance control. But however, to vary the voltage V, we must be having a variable DC voltage source, okay. That we will see a little later. Now, what if we vary the field flux phi here? So, the third method is the field control. Or field current control. So, what we have here is that we have this motor, armature here, let us say it is separately excited, this is V and this is also V here, the voltage here. Now, this is the field resistance RF and we change the field current. Now, if we remember the torque speed characteristic omega m is equal to V by K phi minus T r by K phi whole square. Now, in this case as you go on varying the field current, what we do here, we change the flux, When we change the flux, both the no load speed and the slope both are affected. Now, let us draw the speed torque characteristic for field control. As per the convention, we take the speed in the y axis, torque in the x axis. Now, let us say we have the voltage, the profile here for the value of flux equal to phi 1. Now, what we do? We reduce the flux here. When we reduce the flux, the no load speed increases and the slope also increases. So, it means if you reduce the flux, we get somewhat this profile, phi is equal to phi 2. and we further reduce the flux phi equal to phi 3. So, what we get here? We get various no load speed, this is omega m naught 1 and we get omega m naught 2 and we have omega m naught 3. Now, this way of control is applied beyond the rated speed. When we decrease the field, in this case phi 1 is greater than phi 2 is greater than phi 3. So, when we reduce the field, the speed increases, and this method of speed control is employed for higher speed. This is employed for higher speed application. Applied for higher speed, especially beyond the rated speed. And if we have a load torque profile here, this is our load torque profile, which is constant load torque, and we see that by having this field control, we have field variation, speed variation. This is one speed omega m 1, and then the second speed, the intersection of the second characteristic with the load characteristic is omega m 2, and then when the flux again decreases, we get still higher speed, which is omega m 3. So, by controlling the field, we get higher speed. So, this is about the shunt motor or separately excited motor control. Now, let us try to see the series motor, how we can control the series motor. Now, in case of a series motor, what we have is the following. We have the armature here, and we have the field in series with the armature. And we apply voltage across the armature. As a result, we have a current here I A, and the same I A is also flowing through the field. Now, let us say the combined resistance is R. R is equal to the armature resistance plus the field resistance. So, the combined resistance of the circuit is R here, and the back EMF which appears across the armature is, let us say, E. Now, when we do this series motor control, we can write down the equation for the series motor. V is equal to, we have the back EMF here E plus I A into R. Now, what is E here? E is the back EMF. So, the back EMF is usually the flux into the speed, k phi into the speed. Now, here the flux is produced by the series field, and flux is a function of the field current, which is same as the armature current. Here we have to note that IF is same as IA. The field current here is same as the armature current. So, what is the flux in this case? Flux here is given as Kf into If, because as you go on varying the field current, the flux will change. This assumes the magnetic linearity. It means, if you assume that the magnetic circuit is linear, when we change the current, field current, flux will change, or the field flux will change proportionately. Now, when we apply this in the equation, again we have the equation for the torque. Torque is given as k phi the flux into the armature current, that is equal to K, and phi is Kf into If, Kf If into Ia, If is same as Ia. So, in that case that is equal to K Kf into Ia square. So, in a series motor, torque is proportional to the square of the current. If you change the current, torque will change quadratically, means the square of the current. Now, let us find out the speed as a function of torque. Now, from this equation, let us say we say this is equation number 1, this is equation number 2, this we will say equation 3 and equation 4 here. Now, from equation 1, we can say that E is equal to V minus Ia into R. What is E here? E is the back EMF, which is K phi omega m, that is equal to V minus IAR. Phi is Kf into Ia omega m V minus IAR, or from this we can say that omega m is V by KKF Ia minus R divided by KKF. So, this is an important equation for series motor. So, this relates the speed with the current, but we ultimately want speed as a function of torque. So, from equation 4 we can say here that T equal to K Kf into Ia square. From this we can say that Ia is equal to under root T by K Kf. So, if you substitute this value of Ia in this equation 5, what we get is the following. So, substituting the value of Ia from equation 4 in equation 5, we get omega m is equal to V divided by K Kf under root T minus R by KKF. Let us have a look at the previous equation. Now, here what we have done here is that we have replaced this Ia by under root T by KKF. So, when we replace this Ia by under root T by KKF, we have a cancellation here, and finally, we get V by under root KKF into under root T minus R by KKF. So, this is what we got in this final equation. So, this equation gives the relationship between the speed and the torque for a series motor. Now, here let us plot this speed torque characteristic. The torque is in the x axis and speed is in the y axis. Now, if we plot it, if torque is let us say 0 here, if you substitute t equal to 0, what happens? If you make t equal to 0, the no load speed, this represents the no load speed, and this is a constant quantity. So, this is of the form we can rewrite this as A divided by under root T plus B, B is a negative quantity. So, it means if T is 0, the speed is infinity. So, it means if the speed is 0, I mean the torque is 0, the speed is infinity. So, it is infinity, and after some time when these two quantities will be same, this and this will be exactly the same. We are increasing the torque. Torque was initially 0. When we are increasing this torque, when these two quantities will be the same, omega m will be equal to 0. So, in that case finally, what we get here is that this is the torque speed characteristic of a series motor. So, it is interesting to note that at t equal to 0, the speed is infinity ideally. So, that is why a series motor should not be started with no load condition. It means, if the torque equal to 0, the speed may reach dangerously high value, which will jeopardize the mechanical parts by applying high centrifugal force. So, a series motor should not be started under no load condition. So, this is the speed torque characteristic. How do you vary the speed? So, let us say we talk about the speed control. Now, same thing here, we can control the armature voltage and the armature resistance. So, we first talk about the resistance control, armature resistance control, armature resistance control. Let us write down this equation once again. Omega m is equal to V by under root k k f under root t minus r by k k f. Now, what we are trying to do here? We are trying to change r. Now, when we are trying to change r, how does the characteristic change? Torque is in the x axis and speed is in the y axis. Let us say we have the original characteristic like this. Okay. At some point it will intersect the x axis at some point. Now, this is corresponding to r equal to r 1. Now, when we increase r, let us say we make r equal to r 2. So, in that case this is a negative quantity, this term will be subtracted from the first term. So, for the same value of voltage and same value of torque, we get a reduced speed. So, it means if r is more, we get a reduced speed. So, we get a reduced speed here. So, this profile will be somewhat like this. This is for r equal to r 1, r 2. Now, we further reduce the value of r, make it r 3, the profile will shift towards the left again, make it again more, the profile will shift like this. So, this is for r equal to r 3 and this profile is for r equal to r 4, and here r 1 is less than r 2, is less than r 3, is less than r 4. So, we are increasing the value of r. So, r is increasing. So, when r is increasing, we naturally have the speed control, because if we have a load torque profile like this, the speed will be decided by the intersection of the load profile and the motor characteristic. This is the initial value of speed, let us say omega m 1. Then for the second characteristic of the motor, when r equal to r 2, we have got omega m 2. Then we have for the third characteristic omega m 3. For the fourth one, we have omega m 4, and this is how we get the speed control. Speed is changing as we are changing the resistance. So, this is very easy to have a rheostat in the armature circuit and change the rheostat, the speed will change. But what is the drawback? The drawback of this method is, as before, is high I square R loss. So, the disadvantage of this method is the following, that I square R loss increases with increase in resistance. Now, let us see another method here, that is the applied voltage control or the terminal voltage control. So, let us see, we have the speed torque characteristic omega m is V by under root k k f into under root T minus R by k k f. In this case, what we are doing here? We are changing V, we are not changing R, we are changing V. So, when we are changing V, what happens? When we are changing V here, this is omega m and the torque y axis and x axis respectively, speed is the y axis, torque is in the x axis. Now, when we have the profile here for some value of the voltage V 1, let us say the voltage changes to V 2. When the voltage changes to V 2, the no load speed changes. It means, if we decrease the voltage, the speed will decrease. So, the profile will be like this, V 2, V 3 and so on. So, in this case V 1 is greater than V 2 is greater than V 3. So, V is equal to V 1, V is equal to V 2 and V is equal to V 3, and in this case the voltage is decreased here V 1 to V 2 to V 3, and we get the characteristic here, and if the load has got constant load torque profile T L, the speed is determined by the intersection of the load with the motor characteristic. So, this is corresponding to the first speed omega m 1. Now, if you reduce the voltage, this is omega m 2, and then if you still reduce the voltage, we get omega m 3. So, this is how we control the speed by controlling the terminal voltage, that is V. Now, yet we have a third method of control, that is called the field control. Now, we write down the equation once again, omega m is V by under root k k f under root T minus R by under root k k f. Now, what do we mean by field control? We have the field in series with the armature. If you see the circuit of the motor, here the field is in series with the armature. So, by meaning of field control, we use a diverter resistance to reduce the effective field current. It means, what we do here, we apply or we connect some resistance in parallel here, so that the field current is reduced through the field winding. If you, this is called the diverter resistance. So, when we put a diverter resistance, the effective field current is reduced here, because this is also taking some current. So, the current flowing through the field winding is reduced. That is how the flux to the field winding will be reduced. So, the field control is also one of the ways of speed control that we will be discussing in the next lecture.